All right, IB AI SL2. We've made it through our first target on probability, and now we're going to do another target on probability, but this one is on probability distributions. Before we get into our problems today, we need to talk about this word discrete. I think we talked about it back in some of our stats units, but just a reminder, discrete data is the result of counting, and it's only integers. Integers is just another word for whole numbers. Those are both positive and negative. So just an example of a discrete probability distribution. You're going to see these tables that look like this guy right here. The way you kind of decode these is like the thing on the top row is like all the possibilities of things that could happen in the problem. Like this problem is the number of failing light bulbs in a factory or something like that. So notice that all of these integers up here are discrete. There's not a 2.5, there's not a 3 or 4. They were, or 3.5 or 3 1/3 or something like that. It's all the result of counting. It's discrete data. Now, down here on the bottom, each of these are the probability of that happening in the problem. So you're going to see sort of some weird notation where they say like probability of capital X equals baby X. Really, the capital X can just be anything. It can be any of these like 0, 1, 2. Like you can set probability of capital X equal to 0. And then this is the probability of that happening within the problem. Each of those probabilities will only be between 0 and 1. So any probability of capital X equaling little x has to be in between 0 and 1, just like all probabilities are always in between 0 and 1. And also all 5 of these have to add up to 1. So every single probability within the problem has to add up to 1. If you take every single situation, add them all together, that's the entire sample space. The whole thing has to add to 1. First up, we're going to show that this function right here is, this t is an element of z. What this means is an element of, and then z is just the fancy letter for integers. So really this is telling us that t is discrete, that there's no decimals, there's no fractions or anything like that. They also tell us that t is only between 3 and 7, so that means t, it could be 3, 4, 5, 6, 7, and that's it. And that's essentially how we're going to build our table, is we're going to start to make a probability distribution table, and we'll put t on the top, and then we'll put f of t on the bottom, which is the function. Because they're only between 3 and 7, we're going to start with 3, 4, 5, 6, 7. And then we're going to find each probability by taking those numbers and plugging them in to this spot right here. Now, when I plug a 3 into this function, 3 minus 2 is 1, and you get 1/15. So the probability of getting a 3, in this case, is 1 out of 15. If you plug a 4 in there, you get a 2 out of 15. If you plug a 5 in there, you get a 3 out of 15. And then a 4 out of 15. And then a 5 out of 15. This would be the probability distribution. You should always check to make sure these add up to 1. So if I take all these and I say 1/15 plus 2/15 plus 3/15 plus 4/15 plus 5/15, all these add up to 5, 9, 12, 14, 15. 15 15s, which indeed does equal 1. So this is a probability distribution, a discrete probability distribution. A cubical die. Cubical just means it has 6 sides. And then a tetrahedral die. Tetrahedral is kind of a funny one, but this is 4 sides. The 6-sided die has the numbers 1 through 6 on it. The 4-sided die has the numbers 1 through 4. They're thrown. Each of the numbers are added together. So we're going to construct a probability distribution table for S. This would be 2, 3, 4, 5, 6, 7. This would be 3, 4, 5, 6, 7, 8. 4, 5, 6, 7, 8, 9. So these are all the possibilities for throwing it. There's 24 different options. So to come up with the probability distribution table, we're just going to count up how many there are of that kind, because there's only 2s, 3s, 4s, 5s, 6s, 7s, 8s, 9s, and 10s. There is 1 2 out of the 24, so this is 1/24. Then, in terms of 3s, there are 2 of them, so this will be 2 out of 24. And then for 4s, there's 3, so this will be 3 out of 24. For 5s, there are 4, this is 4 out of 24. Then for 6s, there are also 4, sorry. Then for 7s, we got another 4. For 8s, there are 3 out of 24. For 9, there are 2. This is 2 out of 24. And then there's 1/10, so this is 1 out of 24. I realized that some of those reduce, that like 4 out of 24 is 1 out of 6, but in terms of like solving certain probabilities in this problem, I think it's fine to leave those like that unsimplified. So we're going to use this table to answer these questions, like the probability of S being greater than 2. The probability of S being greater than 2, there's so many different ways for that to happen, like 3, 4, 5, 6, 7, 8, 9, 10. I think the quickest way to do this is do 1 minus the probability that it is 2, because that's the only other thing in the sample space. So this would be 1, take away 1/24, which is 23 out of 24. The next problem, the probability that S is at most 6. Now, at most 6 means that it's all of this in the table. It's 2, 3, 4, 5, 6. So we're going to take each of these probabilities and add them together. So this is 1 out of 24 plus 2 out of 24 plus 3 out of 24 plus 4 out of 24 plus 4 out of 24. Which I believe is, let's see, 3, 6, 16, 20 out of 24. But then our final answer like that should be reduced. Did I do that right? 3, 6, 10. Oh, sorry, that's 14. My bad. Which reduces down to 7/12. So your final answer should be reduced all the way. The last question, probability is of that S is less than or equal to 6 given that S is greater than 2. Using that formula we learned, this means that this is the intersection of the two things on top. Divided by just the probability of the second thing. Now, the probability, the intersection on top, that S is less than or equal to 6 and S is greater than 2, that is, okay, greater than 2. I'm going to use a different highlighter. Greater than 2 does not include 2. So if it's greater than 2 and less than or equal to 6, then we're talking about these right here. So the top is going to be 2/24. Here, I'll do a little zoom out. 2/24 plus 3/24 plus 4 24ths plus 4 24ths, all on top. And then on bottom, the probability that S is greater than 2, we already figured that out. It's up here in part A. So that's, 23 24ths on the bottom. Now to simplify this whole thing, let's see, on top here, we get 2, 5, 9, 13 24ths, all divided by 23 24ths. Now, anytime you have a fraction divided by a fraction, you keep the top fraction as it is. So this is 13 24ths, but then you multiply, instead of divide, by the bottom fraction upside down. So this will be times 24 over 23, which is 13 23rds because the 24s cancel out. And that is our final answer for that problem. All right, you guys, good luck. Ask me questions in class.